Welcome to the fourth lecture for Modern Aspects of Nuclear Chemistry. This lecture is on the chemistry of neptunium. The readings are the neptunium chapter in the chemistry of the actinides and transactinides. This link will be on the website. In this lecture we're going to talk about the production of neptunium isotopes and their nuclear properties. We're going to see that the longest lived isotope, neptunium-237, is the primary isotope used in exploring its chemistry. We'll also talk about the aqueous phase chemistry of neptunium. Like uranium, the compound that is most often found in the aqueous solution phase is the eel component, so neptunium. Unlike uranium, which is +6, neptunium tends to be in the +5 oxidation states, so it's NPO2+. That's one of the major differences, and that drives a lot of the differences in the chemistry. But the other thing we're going to see is that the other oxidation states of neptunium, the 4 and the 6, are also accessible, particularly when you compare to uranium, where the 5 oxidation state in solution was not very readily available. In neptunium, we're going to have the 5 readily available, plus the 4 and the 6, which means that the chemistry can be more complicated. And with separations and purifications, we're going to see that any changes in the neptunium oxidation state will also impact separation and purification. We'll also talk about the metallic state of neptunium, compounds, structure and coordination chemistry, and we'll end this lecture discussing the analytical chemistry of neptunium. Neptunium has 22 known isotopes. The longest lived is the neptunium-237 isotope, which can be produced two ways in the nuclear fuel cycle. One is consecutive capture on uranium-235. Uranium-235 captures a neutron as instead of fissioning, in a smaller percentage of the time it'll capture the uranium-236. The uranium-236 is also long-lived, and it can capture a neutron and create uranium-237, which then beta decays to neptunium-237. There's also this N-to-N reaction on uranium-238, creating the uranium-237, which then beta decays to neptunium-237. And then lastly, in the nuclear fuel cycle, you can have formation of americium-241 from the beta decay of plutonium-241. The alpha decay of americium-241 creates neptunium-237. Neptunium-237, one of the main uses of it is for the formation of plutonium-238. Plutonium-238 is a very good heat source for producing batteries that can be used for remote applications such as space exploration. Neptunium-238 and Neptunium-239 are also available. Neptunium-239, as we've already discussed, is a relatively short-lived half-life, but it does have a nice gamma line that can be used for radio tracers. And then Neptunium-235 and 236 can be produced from cyclotron irradiations of uranium-235. Neptunium has a range of oxidation states that are available in solution, from the +3 to the +7. The most stable oxidation state, as we'll see, will be the +5. However, other states can be stabilized based upon acidity, ligands available, and even the neptunium concentration. Similar to uranium, +5 and +6 oxidation states form dioxyl cations, as shown here. The redox potentials for neptunium have been evaluated, and the data is presented here. In basic solutions, there's some difficulty in evaluating the data due to the complex chemical speciation that occurs. Zane's data, which is shown here, where you have the absorption edge of different neptunium species as a function of oxidation state present. And we see the neptunium-3 absorbs early, the 4 here, the 5 and the 6, they have a behavior that's indicative of this eel oxygen. And this information can be used to determine the ratio of different oxidation states in the solutions examined, and by using the Nernst equation, the redox potentials can be determined. In solution, neptunium can undergo disproportionation. For example, neptunium-5 can form neptunium-4 and neptunium-6 in solution. The equation here shows the reaction that occurs, where neptunium-5 with acid can go to neptunium-4 and neptunium-6. So this disproportionation is favored in high acidity and high neptunium concentrations. So if you wanted to limit disproportionation in a solution, you would limit both the neptunium concentration of the pentavalent oxidation state and the acidity. So there's an importance of understanding the oxidation state in neptunium since it dictates the chemistry. Here's presented some routes for preparing specific oxidation states of neptunium. So the 6, the 4, the 5, and the 3. The fundamental approach is to take a mixture of oxidation states and either oxidize the system completely to one oxidation state or reduce to a lower oxidation state. So for example, if one wanted to take a mixture and make it into neptunium-5, you could oxidize everything to neptunium-6, then take neptunium-6 and reduce that to neptunium-5. This information is important particularly in separations where neptunium may not, in separation systems, they may not want neptunium to extract. So neptunium-5 will not extract in a Purex environment with tributyl phosphate. However, if neptunium oxidizes to the 6 or reduces to the 4, it can extract. So work has been performed evaluating redox control of neptunium in Purex systems. So hydroxylamine nitrate and its derivatives were used for neptunium-6 reduction to the 5. And this is found to be a first order rate with excess reductant. This complex solution chemistry of neptunium can be explored for the range of the oxidation states. Detailed modeling has been explored with neptunium-5, looking at the spin orbit coupling of the two 5F electrons. Obviously, since the neptunium species are colored, UV visible spectroscopy can be a useful tool in evaluating its speciation. And as an example here, in 2 molar perchloric acid, neptunium-3 has an absorbance of around 780 nanometers with an extinction coefficient of 45. Tetravalent neptunium, a little bit higher at 960 with a larger extinction coefficient. The prominent oxidation state in solution, neptunium-5, has a very large molar absorptivity, close to 400, and is in the near IR region, close to 1,000. And neptunium-6 is over 1,000, 1,200 nanometers, with a molar extinction coefficient of 45. Neptunium-7 is available only in basic media, and the absorbance has been examined, including vibrational states, since you have these neptunium-oxygen bonds. A range of complexation constants have been evaluated for neptunium with a number of inorganic ligands, and the trends are similar to other metal ions. So observed here, fluorine being strongest, perchlorate being the weakest. And as we discussed with uranium, neptunium can also form cation-cation interactions where the oxygen from neptunium can coordinate with metals listed here, going in strength from iron down to aluminum. The neptunium solution chemistry can also be explored through hydrolysis. The hydrolysis preference is the same as for uranium, where the tetravalent is the greatest propensity to hydrolyze, the pentavalent the least. The data for the hydrolysis is listed here, and what's shown here is a speciation curve of neptunium-3, 4, 5, and 6 as a function of pH. And this data was collected with CHESS, and these complexation constants are available in the CHESS database. We've already discussed the importance of neptunium redox speciation in the Purex separation.
Again, neptunium-5 is not extracted. However, we've also discussed that neptunium-5 can solely disproportionate in high acid, one of the conditions of the Purex process, where it can form extractable neptunium-4 and neptunium-6 species. Studies have been performed to understand this redox behavior, and reduction of neptunium-6 by a range of compounds have been explored. One of these compounds is acetohydroxamic acid, which is shown here. And acetohydroxamic acid has preferentially shown to complex with tetravalent species, including tetravalent neptunium and plutonium, and this has been used to help control its behavior in proposed separation systems. The back extraction of neptunium-5 can be used also to control plutonium and uranium during the separation process, particularly through controlled neptunium-6 reduction in the presence of plutonium-3. Again, plutonium-3 is an extracted species from the organic phase and is one of the main goals of the Purex process for the separation of plutonium from uranium. We've already discussed the solvent extraction-based methods using tributyl phosphate, where, very similar to the uranium, we get the neptunium-6, 2-nitrate tributyl phosphate, and as we'll see with plutonium, the neptunium-4 with 4 nitrates tributyl phosphate system extracted. Data is shown here for the extraction of tetravalent neptunium and hexavalent neptunium. CMPO, which is a ligand that is preferentially used in the Truex process, has also been studied with tributyl phosphate, and separations have been achieved with oxidation state variation, where neptunium and plutonium can be reduced and neptunium-4 can be extracted into organic and then removed with the carbonate oxalate, or EDTA. Other neptunium solvent extractions include the use of HDEHP, which is the molecule shown here. This is also part of processing for actinides. In this case, with 1 molar nitric acid with the addition of sodium nitrite, the uranium, plutonium, neptunium, and americium go into the most stable oxidation states. In this case, neptunium-5 is not extracted. So we get oxidized material, we can extract, and then if neptunium is reduced back to the 5, it can be back extracted into 1 molar nitric acid. Trianoctylamine is also used, and this has been exploited for separation of neptunium from environmental samples, where you can extract the neptunium in 10 molar HCl, and then back extract it with weaker HCl and a little bit of HF. Combinations of ligands, synergistic extractions with CMPO and tributyl phosphate in dodecane have also been performed. And as we can see here, we can vary the distribution coefficients, so depending upon the oxidation states. And if we examine a system such as 1 molar nitric acid, this mixture of CMPO and tributyl phosphate has a very high extraction for neptunium-6, extremely low for neptunium-5, and above 1 for neptunium-4. So here's a clear example of how the role of the neptunium oxidation state will vary the extraction behavior as a function of acid concentration. Now we can start exploring chemical forms of neptunium that have some relevance to the nuclear fuel cycle. One would be metallic neptunium. This was first synthesized from neptunium trifluoride with barium metal at elevated temperature. Current methods are very similar to the uranium methods, where you can use group 1 or group 2 elements or a molten salt process for producing neptunium metal. So here's something where neptunium dioxide is dissolved in a molten salt. Through electrolysis, one can reduce the neptunium-4 all the way to the metallic state. Work has also been performed in the laboratory on using mercury, making amalgams of neptunium. This also works with uranium and plutonium from an acetic acid solution, and then the mercury can be distilled to produce pure metal. Neptunium has a melting point of around 600 degrees C, extremely low melting point, has a very high density, close to 20. There's 3 metallic forms. The transition temperatures are listed here for the alpha to the beta, around 500 K, and the beta to the gamma, around 850 K. The symmetries of the groups have been identified: orthorhombic, tetragonal, body-centered cubic. And we see this trend again with, compared to uranium, where we went from symmetries and at higher temperatures ended with something similar to body-centered cubic. The oxides of neptunium are important compounds for the nuclear fuel cycle. However, unlike uranium, there are only 2 known oxide species. Remember, with uranium we had primarily UO2, U3O8, UO3. For neptunium we have NP2O5 and the dioxide, NPO2. NPO2 is the stable oxide, and it can be formed from the thermal decomposition of a range of neptunium compounds, and it has the same sort of structure as the other actinides, so we would expect neptunium dioxide and uranium dioxide to form solid solutions. This compound is stable over a range of temperatures, and the phase diagram, where we look at the phases as a function of temperature against the oxygen to neptunium ratio, is shown here. And comparing this to the uranium phase diagram, we see many fewer species. Now, NP2O5 can be formed from the thermal decomposition of neptunium-6 or neptunium-5 hydroxide. However, this material, if you make the NP2O5, it decomposes to the NPO2 between 700 and close to 1000 K. The halides are also important species. You can make neptunium halides to the 3, 4, 5, and 6 oxidation state. And these can be prepared from the reactions with HF, as shown here, either starting with the dioxide or taking the fluoride, the tetrafluoride, adding another fluoride to it, taking the dioxide and reacting it with the fluoride directly to make the tetrafluoride. Like uranium hexafluoride, neptunium hexafluoride is volatile, and it actually has a higher vapor pressure than both the uranium and the plutonium compound. The synthesis is similar to what we discussed for the uranium hexafluoride compound. Neptunium tetrachloride can be formed from the dioxide with carbon tetrachloride, and then the trichloride can be formed by treating the tetrachloride with hydrogen. This is similar to the uranium reaction. The bromide can be formed by reacting the dioxide with aluminum tribromide. And if you take the elements, neptunium and iodide, they can also form neptunium iodide. Same thing with bromide, neptunium, and bromide. These reactions are all similar to the uranium species. However, the measured data on the neptunium compounds is much more limited than the uranium homologs. An area of fundamental chemistry that involves neptunium is coordination chemistry. And this interest is driven by the different oxidation states that neptunium has and the ability to perform systematic studies of the actinides. For neptunium-3 coordination compounds, there's very little data due to the instability in aqueous solutions under air. Neptunium-4, there's been a few compounds formed, and they find to be isostructural with the uranium-4 complex. Neptunium-5 is shown to undergo cation interactions. Neptunium-6, there's been some simple synthesis, for instance with oxalic acid and neptunium-6 solutions. However, over time, these compounds will show reduction of neptunium from the hexavalent oxidation state. And then for neptunium-7, there's some literature available, but there tends to be disagreement over the exact neptunium-7 species that are in these coordination compounds. An example of neptunium organometallic chemistry is shown here, and it's mainly done with the cyclopentadienyl species, demonstrated here, which has actually been performed for the other actinides. The synthesis route is shown here, where you can take neptunium CP chloride with some sodium, drive a reduction to get the neptunium-3 tri-CP in tetrahydrofuran. It has been found difficulty to remove the tetrahydrofuran from this compound, so there's strong coordination still in that environment. In neptunium-4, a similar synthesis, again with a chloride starting compound, where we can get the 4 CP ligands around the neptunium. This dissolves in benzene and tetrahydrofuran and could allow spectroscopic examination of this material to be performed. Finally, there's some analytical methods that can be used for determining neptunium. Most common you would expect would be radiometric methods. For the alpha, there's 2 times 10 to the 7th becquerel per gram. So this allows a way to detect the neptunium. Isolation of neptunium from seawater can be performed. Usually the material is concentrated with coprecipitation ion exchange or in solvent extraction. Liquid scintillation has also been used, obviously as an extension of alpha spectroscopy. Another interesting route is the formation of neptunium-238 by the neutron capture on neptunium-237, so neutron activation analysis. And this has the capture cross-section is high, 170 barns, and the half-life of the neptunium is very short, 2.117 days. So this allows for a very sensitive route for the determination of neptunium, and it's found to be 500 times more sensitive than alpha spectroscopy. Spectrophotometric routes are available, as we've already discussed. Based upon the molar absorptivities, these concentrations can be observed in UV visible spectroscopy in a 1 centimeter cell with an absorbance down to 0.02. So neptunium-5 you can almost get down to micromole per liter. Fluorescence has also been explored. These are usually performed at low temperature. Data has been collected that shows that neptunium can fluoresce. And of course, X-ray fluorescence and mass spectroscopy are useful tools in neptunium analytical methods. A review of an analytical method we discussed during gamma spectroscopy is Mossbauer spectroscopy. So the excitation is done with americium-241, and this is just a review of what we've already discussed. This shows that one can identify different species of neptunium through its Mossbauer spectrum. So as a review, this presentation discussed the role of oxidation states of neptunium in solution, how those oxidation states can be adjusted, and how it influences the chemistry, particularly its separation chemistry. The main fact being that neptunium-5 is the dominant oxidation state in solution. However, the oxidation state can change over time and conditions, particularly with disproportionation of neptunium-5 going to neptunium-6 and 4, where both these oxidation states can be extracted.
Some of the questions you should be able to answer based on this lecture are listed here. What's the primary solution phase oxidation state of neptunium? Neptunium is pentavalent, plus 5. But that compound is the dioxide neptunyl, as shown here. What is the neptunyl disproportionation reactant, the neptunium-5? Well, neptunium-5 with acid goes to neptunium-4 plus neptunium-6. We have 2 neptuniums going to a 5 going to a 4 and a 6, so there's no net change in overall oxidation state. This is also a condition that one can evaluate to determine how to keep neptunium-5 stable in solution. One would be not store it under acidic conditions and try to keep the concentration low. How does this neptunium disproportionation reaction impact the Purex process? We introduced the Purex process in this lecture. We'll have some details on this process in lecture 17. But the process is used to remove uranium and neptunium from spent fuel. If neptunium is, during the separation process, neptunium is not extracted product, neptunium-5 does not extract in the Purex process. However, the process is acidic, so you can get disproportionation of neptunium to the 4 and to the 6 oxidation state, and both these extract. So in this high acidity process, neptunium-5 does not extract, neptunium-4 and 6, so that is in plutonium-4 and uranium-6, they extract in the Purex process. So if neptunium undergoes disproportionation, it can actually go in both the aqueous and the organic phase of the process. And then finally, another example of a question is, what are the neptunium binary oxides? Unlike uranium, where we saw many uranium oxide species, for neptunium we only see 2, this neptunium-5 NP2O5 and this neptunium-4 NPO2 compound. When you have completed this lecture, please provide comments on the blog and respond to the PDF quiz 4 on neptunium.